Welcome back to another fascinating journey through the world of modern manufacturing with Sky Creative Channel. Today, we're taking you inside some of the most impressive production facilities around the globe. And we're starting with something that's been the backbone of industry for over a century, steel production. Let me tell you about Gruppo Pittini, an Italian steel giant that's been perfecting the art of wire rod production since 1960. Now, if you remember the steel mills of yesteryear, those roaring furnaces and the glow of molten metal, you're going to appreciate how far we've come with modern technology while still honoring those fundamental principles. Wire rod production at Pittini begins with something called an electric arc furnace, or EAF. This isn't your grandfather's blast furnace. Instead of using coal and iron ore, these modern marvels recycle scrap steel, melting it down at temperatures exceeding 3,000 degrees Fahrenheit. The EAF uses massive electrical currents. We're talking about the power needed to run a small city to create an arc between giant graphite electrodes and the metal below. It's like lightning in a bottle, and it melts tons of scrap steel in less than an hour. Once molten, the steel flows into a ladle furnace, where metallurgists fine-tune its chemistry. Think of this like a chef adjusting a recipe. They're adding precise amounts of carbon, manganese, and other elements to achieve exactly the properties needed for the final product. This is where science meets art, and it's fascinating to watch these specialists work. The next stop is the continuous casting machine, and this is where things get really interesting. Back in the old days, steel was poured into individual molds and had to cool completely before processing. The continuous casting system revolutionized everything when it was developed in the 1950s. At Pittini's facility, molten steel pours continuously into a water-cooled copper mold, forming a solid outer shell while the inside remains liquid. As it exits the mold, the steel billet, that's a square or rectangular bar, continues through a series of rollers and water sprays that gradually cool and solidify the center. It's pulled along at a steady pace, like an infinite loaf of bread being formed, then automatically cut into manageable lengths. These billets then head to the reheating furnace, where they're brought back up to about 200 degrees Fahrenheit. Why reheat them? Well, steel needs to be at just the right temperature for the rolling process. Hot enough to deform easily, but not so hot that it loses its structural integrity. Now comes the heart of the operation, the rolling mill. This is a series of stands, each containing powerful rollers that progressively squeeze and elongate the steel. The billet enters as a thick square bar and goes through up to 20 or more rolling stands. Each pass reduces the diameter and increases the length, transforming that chunky billet into a thin, flexible wire rod. As the wire rod exits the final rolling stand, it enters a cooling system. Pittini uses what's called controlled cooling, where water sprays and air jets bring the temperature down in a precisely managed way. This isn't just about cooling it off. The cooling rate actually determines the final properties of the steel. Cool it too fast, and it becomes brittle. Too slow, and it might be too soft. Finally, the wire rod is formed into coils by a laying head, a spinning mechanism that loops the wire in perfect circles as it comes off the line. These coils, weighing up to 2 tons each, are then bound, labeled, and prepared for shipment. This wire rod will go on to become everything from tire reinforcement to construction mesh, from springs to fasteners. What really impresses me about Pittini's operation is the integration of automation and quality control. Throughout the entire process, sensors monitor temperature, speed, dimensions, and chemical composition. Computer systems make real-time adjustments, ensuring every coil meets exacting standards. It's a far cry from the days when mill workers relied on the color of the steel to judge its temperature. Now let's shift gears and talk about precision machining. If steel production is about power and heat, CNC turning is about accuracy and finesse. We're looking at the CTX Delta 4000-6000 TC from DMG MORI, operated by VMC CNC. And folks, This machine represents the pinnacle of modern turning technology. The CTX Delta series is what we call a twin-spindle, twin-turret machine. Let me break that down. Traditional lathes have one spindle that holds and rotates the workpiece. This machine has two spindles facing each other, and they can pass the part between them. It's like having two complete lathes, working in perfect coordination. Each spindle also has its own turret. That's the tool holder that can carry up to 12 different cutting tools. Here's where it gets clever. While the main spindle is working on one end of a part, the counter spindle can be loading the next piece. When the first operation is complete, the counter spindle grabs the part, flips it around, and immediately starts working on the other end. No waiting, no manual handling. The efficiency gains are enormous. The turning process itself is mesmerizing to watch. The workpiece spins at speeds up to 5,000 RPM. That's over 80 revolutions per second, while cutting tools approach from multiple angles. These aren't ordinary drill bits. They're precision ground inserts made from carbide or even diamond, capable of removing metal while maintaining tolerances of just a few microns. What makes the CTX Delta special is its rigidity and thermal stability. The machine bed is made from a special cast iron that's been aged and stress-relieved, minimizing distortion. The linear guides use preloaded ball bearings that eliminate play while allowing smooth, precise movement. Temperature control systems keep the machine at a constant temperature, because even a degree or two of thermal expansion could throw off those tight tolerances. I've always found it fascinating how CNC technology democratized precision manufacturing. In the old days, producing complex turned parts required years of training and experience. Today, a programmer can create intricate components that would have been impossible to make consistently by hand. Yet, there's still an art to it, knowing how to set up tools, selecting the right cutting parameters, and troubleshooting when things don't go quite right. Let's head to the water now and talk about something that's been propelling boats since the 1830s, the propeller. Yamaha Outboards, a name synonymous with marine excellence since 1960, has refined propeller manufacturing into a precise science, and the production process is absolutely fascinating. The manufacturing process starts with precision casting. Yamaha uses investment casting, also called lost wax casting, a technique that dates back thousands of years but has been perfected with modern technology. First, a wax pattern is created, an exact replica of the final propeller. This pattern is dipped repeatedly in a ceramic slurry, building up a shell around it. Once the shell hardens, the wax is melted out, leaving a perfect cavity. Molten stainless steel, heated to over 700 degrees Fahrenheit, is poured into this ceramic mold. The metal fills every tiny detail of the cavity, capturing the complex curves and surfaces that make a propeller work. After cooling, the ceramic shell is broken away, revealing the rough casting inside. But we're far from finished. That raw casting goes through extensive machining to achieve the precision needed for optimal performance. CNC machining centers mill the hub to exact dimensions, ensuring it fits perfectly onto the propeller shaft. The bolt holes are drilled with precision positioning. Any misalignment could cause dangerous vibration at high speeds. The blades receive special attention. Each one is machined to maintain the exact hydrodynamic profile designed by Yamaha's engineers. We're talking about curves and angles measured in fractions of a degree. The leading edges are sharpened, the trailing edges refined, and the blade surface is polished to reduce drag. Here's something interesting. Yamaha uses a process called cupping on many of their propellers. This involves bending the trailing edge of each blade slightly, creating a cup shape. This small modification, pioneered in racing propellers back in the 1950s, helps the prop grip the water better and reduces ventilation. That's when air gets sucked down from the surface, causing the prop to spin wildly and lose thrust. The propellers also undergo X-ray inspection to detect any internal flaws in the casting, tiny air bubbles, or inclusions that could become failure points under stress. Dimensional inspection ensures every critical measurement meets specifications. A coordinate measuring machine probes hundreds of points across the propeller's surface, comparing the actual part to the computer design. Finally, the propellers receive surface finishing. Some are polished to a mirror shine, which reduces drag and looks beautiful. Others get special coatings for enhanced corrosion resistance in harsh saltwater environments. What really strikes me about Yamaha's process is how they've maintained craftsmanship while embracing automation. Yes, robots handle the heavy lifting, and CNC machines do the precision work, but skilled technicians oversee every step, using their experience to ensure quality. Now we're going to explore one of the most versatile manufacturing processes in the modern world, aluminum extrusion. ILSCO Extrusions, based in Cincinnati, Ohio, has been masters of this craft since 1957, and watching their process is like seeing industrial Play-Doh in action, except we're working with metal at nearly 1,000 degrees. The process begins with aluminum billets, solid cylindrical logs of aluminum alloy, typically 8 to 10 inches in diameter and up to 30 inches long, weighing several hundred pounds each. These aren't pure aluminum. They're carefully formulated alloys with elements like magnesium, silicon, and copper added to provide specific properties like strength, corrosion resistance, or machinability. These billets are loaded into a massive induction heating furnace, where they're brought up to temperature, usually between 800 and 950 degrees Fahrenheit, depending on the alloy. This is hot enough to make the aluminum soft and plastic-like, but not so hot that it melts. The heart of the extrusion press is something to behold. ILSCO operates presses capable of generating forces up to 3,000 tons. That's 6 million pounds of pressure. The heated billet is transferred from the furnace into the press cylinder, where a massive ram or plunger pushes it forward. Here's where the magic happens. At the front of the cylinder sits the extrusion die, a thick steel disc with an opening cut in the exact shape of the desired profile. As the ram pushes forward with enormous force, the soft aluminum has nowhere to go but through that die opening. It could be a simple angle or channel, or an incredibly complex shape with hollow sections, multiple cavities, and intricate details. As the aluminum exits the die, it's incredibly hot and soft. It immediately enters a cooling zone where air or water quenches it to stabilize the shape. The extrusion is pulled along by a puller that grips it gently but firmly, maintaining constant tension. The extruded length then moves to a stretcher, and this is an important step many people don't realize happens. The stretcher grabs both ends of the extrusion and pulls it straight with carefully controlled force. This accomplishes two things. It straightens any warping that occurred during cooling, and it relieves internal stresses that could cause problems later. The stretching force is precisely calibrated for each profile and alloy. Next comes the aging oven, where many aluminum alloys undergo heat treatment to develop their full strength. The extrusions are heated to a specific temperature and held there for a precise time, allowing aluminum and alloying elements to form microscopic structures that dramatically increase strength. This process, called precipitation hardening, was discovered back in 1906 and revolutionized aluminum's usefulness. Finally, the extrusions are cut to length on precision saws, and many receive additional operations like drilling, punching, or machining. Every piece is inspected to ensure it meets dimensional tolerances and quality standards. What I find remarkable about ILSCO's operation is the combination of brute force and fine precision. We're talking about thousands of tons of pressure, yet producing parts with tolerances measured in thousandths of an inch. Let's talk about something that's literally building our world: precast concrete. Weckenmann, a German engineering company that's been innovating in concrete technology since 1968, has developed turnkey precast concrete plants that represent the cutting edge of construction manufacturing. Weckemann's turnkey plants are fully integrated production facilities designed to manufacture everything from building panels and beams to specialized architectural elements. The genius is in the automation and precision they've achieved in what was once a very manual process. The process begins with batching, measuring and mixing the concrete ingredients. Modern batching systems are computer-controlled with incredible accuracy. Cement, aggregates like sand and gravel, water, and various admixtures are weighed to within a fraction of a percent. This precision is crucial because concrete strength, workability, and durability all depend on getting the mix exactly right. The mixing itself happens in high-intensity mixers that ensure complete homogeneity. These aren't the old drum mixers you might remember from construction sites. These are planetary mixers, or twin-shaft mixers, that thoroughly blend the materials in just a couple of minutes, creating a consistent, workable concrete. The mixed concrete is then transported to casting stations. Here's where Weckenmann's systems really shine. They use various casting methods depending on the product. Steel reinforcement is precisely positioned, often using robotic placement systems that follow computer models to ensure the rebar is exactly where engineers designed it to be. The concrete consolidation process is critical. Air bubbles trapped in concrete create weak spots, so Weckenmann systems use vibrating tables that shake the forms at precisely controlled frequencies. This causes the concrete to flow and settle, eliminating voids while avoiding over-vibration that could segregate the mix. Many precast elements require steam curing to accelerate strength development. Weckenmann designs curing chambers where temperature and humidity are precisely controlled. The elements are gradually heated to around 150 degrees Fahrenheit and held there for several hours. This accelerated curing allows pieces to be demolded and handled in less than a day, compared to the week or more required for conventionally cured concrete. The demolding process in a modern precast plant is something to see. Automated systems lift panels, rotate beams, and separate products from their forms with mechanical precision. Magnetic or vacuum lifting systems handle pieces weighing several tons with ease. After demolding, products move through finishing stations where surfaces are ground smooth, inserts are installed, and any necessary holes or openings are cut. Weckenmann integrates CNC cutting systems that use diamond blades or water jets to create precise openings for windows, doors, and utilities. What impresses me most about Weckenmann's approach is how they've transformed concrete from a material poured on muddy construction sites into precision-manufactured building components produced in clean, efficient factories. Let's wrap up our journey with something that quite literally makes the world go round gears. The Gleason Corporation has been the gold standard in gear manufacturing since 1865, and their 1500G Titan represents over 150 years of accumulated knowledge applied to modern precision machining. The 1500G Titan is specifically designed for cutting bevel gears. Those are the cone-shaped gears that transfer motion between shafts at an angle, like in your car's differential. Every time you go around a corner, bevel gears are allowing your wheels to turn at different speeds while still receiving power. The cutting head holds a circular cutter with multiple blades arranged around its circumference. Gleason pioneered this face milling process in the 1930s, and it revolutionized bevel gear production. The cutter rotates at high speed, typically 500 to 1000 RPM, while simultaneously rocking back and forth in a precise motion called a generating roll. This motion creates the complex curved tooth surface that allows bevel gears to mesh smoothly and transmit power efficiently. Here's what's remarkable. As the cutter rocks and rolls, the workpiece also rotates in precise synchronization. The machine is calculating and coordinating 6 axes of motion simultaneously, all controlled to within microns. The Titan's structure is built like a battleship to handle the cutting forces involved. The machine bed is a massive casting designed to absorb vibration. The spindles ride on hydrostatic bearings. Instead of metal-on-metal contact, a thin film of pressurized oil supports the spindle, providing both rigidity and zero wear. These bearings were developed for ultra-precision applications, and they're one reason the Titan can maintain accuracy over millions of cutting cycles. Temperature control is another critical factor. The machine generates heat from cutting and from the motors driving all those moving parts. Gleason incorporates thermal compensation systems that measure temperature at strategic points and automatically adjust positions to counteract thermal growth. The coolant system doesn't just cool the cutting zone, it's precisely temperature controlled to maintain the entire machine at a stable temperature. The cutting process itself is fascinating to watch. As the cutter engages the gear blank, it generates a controlled amount of tooth depth with each pass. Multiple passes are often required, starting with roughing cuts that remove material quickly, then finishing passes that achieve the final accuracy and surface finish. The machine automatically changes cutting parameters between passes, optimizing for either material removal or precision as needed. Modern Gleason machines incorporate closed-loop measuring systems that can check the gear right in the machine. Probes measure tooth geometry and compare it to the design specifications. If corrections are needed, the machine can automatically adjust parameters for the next piece. This kind of in-process measurement would have been unthinkable in the mechanical era. What really sets the Titan apart is its versatility. Using different cutter designs and adjusting the machine's motion parameters, it can produce straight bevel gears, spiral bevel gears, zero gears, and hypoid gears, each type optimized for different applications. It's like having 4 specialized machines in one.